Imagine two dancers spinning together. One dancer is much larger, much heavier. That's Earth. The other is smaller, lighter. That's the Moon. They're holding hands, spinning around each other, locked in an eternal waltz. Now here's the key. The smaller dancer, the Moon, spins on its own axis at exactly the same rate that it orbits around Earth. One rotation, one orbit, perfectly synchronized. This means that the same side of the Moon always faces Earth. Always, every single orbit, every single night, for billions of years. It's called tidal locking, or synchronous rotation. And it didn't happen by chance. It happened because of gravity. Billions of years ago, when the Moon was young, probably formed from a massive collision between Earth and a Mars-sized object, it spun much faster. It had days and nights, just like Earth does. But Earth's gravity was pulling on the Moon, not evenly, but more strongly on the side closest to Earth. Over millions of years, this gravitational pull acted like a brake. It slowed the Moon's rotation, little by little, degree by degree, until finally the Moon's rotation matched its orbit, locked, synchronized. One face always toward Earth, one face always turned away. And that's where we are now. The Moon completes one rotation on its axis in about 27.3 days, and it completes one orbit around Earth in 27.3 days, perfectly matched. So when you look up at the Moon tonight, you're seeing the near side, the side that has always faced Earth, the side that ancient humans saw, the side that inspired myths and calendars and poetry and songs. But on the other side, the far side, there is a landscape that has never been visible from Earth. Not naturally, not without spacecraft. A hidden hemisphere, a secret face. And for thousands of years, humans could only wonder, what's over there? Some imagined it was smooth. Some imagined it was identical to the near side.
Some imagined alien cities, or vast oceans, or mysteries beyond comprehension. But the truth is stranger and more beautiful than any of those guesses. Take a moment, breathe. Imagine the Moon, rotating slowly, always showing Earth the same face, keeping the other face hidden. Imagine the patience of that, the constancy, billions of years of keeping a secret. And now, imagine that secret is about to be revealed. The first humans to see the far side of the Moon were not standing on Earth. They were not looking through telescopes. They were floating in a tiny spacecraft, farther from home than any human had ever been. The year was 1959. The spacecraft was Lunar 3, a Soviet probe about the size of a washing machine. It was October 7th, and it was about to change everything. Lunar 3 was on a looping trajectory around the Moon. As it swung around the lunar far side into the region where no human eye had ever peered, its cameras activated. Primitive by today's standards, grainy, low resolution, but historic. The camera clicked, once, twice, 29 times in total, and for the first time in history, the hidden face of the Moon was captured on film. The images were transmitted back to Earth. Scientists in the Soviet Union gathered around screens, holding their breath. What would they see? And when the images appeared, blurry, rough, but unmistakable, the room fell silent. Because what they saw was not what they expected. The far side of the Moon looked different, very different. On the near side, the side we see from Earth, there are large dark plains, We call them Maria, which is Latin for seas. They're not actually seas, of course. They're vast plains of ancient volcanic rock, solidified billions of years ago. They give the moon its characteristic appearance, the bright highlands, the dark Maria, the pattern we call the man in the moon. But on the far side, there were almost no Maria, just a few small patches.
Instead, the far side was covered, absolutely covered in craters, thousands of them, overlapping, layered, ancient impact scars piled on top of each other like a cosmic battlefield. The far side of the moon was rough, scarred, battered, a landscape of violence frozen in stone. Why? Why was the far side so different? The answer is still debated, but the leading theory has to do with the moon's formation and the thickness of its crust. When the moon formed about 4.5 billion years ago, its surface was molten. Over time, it cooled, and as it cooled, lighter minerals floated to the top, forming the crust. But the crust didn't form evenly. On the far side, the crust ended up thicker, perhaps because the moon's center of mass is slightly offset toward Earth. Later, during the period called the Late Heavy Bombardment, about 3.9 billion years ago, the solar system was filled with debris, asteroids, comets, leftover material from the planet's formation, and they rained down on the moon. Both sides of the moon were hit, but on the near side, where the crust was thinner, some of those massive impacts cracked through the crust and allowed molten lava to flow out from below. That lava filled the impact basins, creating the dark Maria we see today. On the far side, the crust was too thick. The lava couldn't break through, so the craters remained, empty, unfilled, just scars. And that's why the two sides look so different. The near side, smooth plains and craters. The far side, almost nothing but craters. It's like the moon has two personalities. One face, calm and familiar. The other, wild and scarred. And for most of history, we only knew the calm face. Take a breath. Let this sink in. The moon, our closest neighbor, was hiding an entirely different landscape. A landscape shaped by the same forces, but expressed in a completely different way. The Soviet scientists who saw those first images understood immediately. This was not just another side of the moon. This was another world. Of course, 1959 was just the beginning. Those first images from Luna 3 were blurry, intriguing, but incomplete, like seeing a face through frosted glass. Over the next decade, more missions followed. Luna 2 had already crashed into the moon in 1959, the first human-made object to reach another celestial body. But it was Luna 3 that gave us the first pictures of the far side. Then came the Americans. In the 1960s, as the space race accelerated, NASA launched the Lunar Orbiter program. 5 spacecraft designed to map the moon in preparation for the Apollo landings. And for the first time, high-resolution images of the far side started coming back. Scientists pored over these images. They gave names to the craters. They mapped the highlands. They studied the composition, the topology, the geology. And they began to understand the far side of the moon was not just different. It was a key to understanding the moon's history. And by extension, Earth's history. Because the moon doesn't have weather. It doesn't have erosion, or wind, or rain. Every impact crater is preserved, almost exactly as it was when it formed. The moon is a time capsule, a fossil record of the early solar system. And the far side, with its thousands of craters, is the most pristine part of that record. Then came Apollo. In December 1968, Apollo 8 became the first manned mission to orbit the moon. 3 astronauts, Frank Borman, Jim Lovell, and William Anders, flew around the moon, seeing the far side with their own eyes. Imagine that moment.
You're in a tiny capsule. You've traveled farther from Earth than any human before you. You swing around the moon, and suddenly, communication with Earth cuts out. You're in radio silence, alone, on the far side. And you look out the window. Jim Lovell described it later. He said the far side looked like a battlefield. A vast, lonely, forbidding expanse of nothing. Crater upon crater. No color. No life.
Just gray stone, stretching to the horizon under a black sky filled with stars. It was beautiful, and it was terrifying. William Anders, the astronaut who took the famous Earthrise photograph, said something else. He said that seeing the far side made him appreciate Earth even more, because when you're on the far side of the moon, you can't see Earth. It's blocked by the moon itself. For the first time in human history, 3 people were in a place where Earth was not visible, not even as a tiny blue dot, just the moon and the stars and the silence. The loneliest place any human has ever been. Take a moment, close your eyes, imagine you're there, floating in space, the moon below you, Earth hidden behind the moon, radio silence. Just you and the void and the ancient scars of a billion impacts. What would that feel like? The Apollo 8 astronauts didn't stay long. They orbited 10 times, then fired their engine and came home. But they brought something back with them. Not rocks, that would come later. They brought back a perspective. They saw the moon's hidden face, and they saw Earth disappear behind it. And they understood, in a way no one had before, how alone we are, how fragile, how precious. That's the power of the far side. It's not just geology, it's philosophy. It's a mirror that shows us who we are by showing us what we're not. So what's actually on the far side of the moon? What is this hidden landscape made of? Let's take a tour. Imagine we're in a spacecraft approaching the moon from behind. Earth is behind us now. We're about to see what only a handful of humans and a few dozen robots have ever seen. First, the craters. The most famous crater on the far side is called the South Pole Aitken Basin. It's one of the largest impact craters in the entire solar system, about 2,500 kilometers across. That's roughly 1,550 miles, and up to 8 kilometers deep in some places. This crater is ancient, probably over 4 billion years old.
It was formed when a massive asteroid, maybe 200 kilometers wide, slammed into the moon at tens of thousands of kilometers per hour. The impact was so violent, it may have punched through the moon's crust and exposed material from the mantle below. Scientists are fascinated by this crater because studying it could tell us about the moon's interior. And since the moon likely formed from Earth, understanding the moon's interior helps us understand Earth's interior. The South Pole Aitken Basin is dark, filled with ancient lava in some places, but mostly just deep, rough terrain. If you stood at the bottom and looked up, the crater walls would rise around you like mountains. You'd be standing in the scar of one of the most violent events in the moon's history, and it's quiet. So quiet. Then there are the highlands. Most of the far side is covered in what scientists call the lunar highlands, bright, rugged, ancient crust. This is some of the oldest surface in the solar system, formed when the moon was still cooling,
over 4 billion years ago. The highlands are heavily cratered. Every square kilometer has been hit, re-hit, and hit again. Some craters are huge, hundreds of kilometers across. Some are tiny, just meters. They overlap, creating a chaotic, fractal landscape of circles within circles within circles. If you could walk across the lunar highlands, you'd be walking on powdered rock, what scientists call regolith. It's not like sand. It's sharp, abrasive, made of tiny shards of glass and stone, created by billions of years of meteorite impacts. It clings to everything. The Apollo astronauts said it smelled like gunpowder. And it's gray, not a warm gray, but a cold, lifeless gray, because there's no atmosphere to scatter light, no blue sky, just black above, gray below. But there are exceptions, small patches where ancient lava did break through. One of them is called Mare Moscoviense, the Sea of Moscow, named by the Soviets who first photographed it.
It's a small, dark patch on an otherwise bright landscape. A reminder that the moon was once geologically active, that it had volcanoes, that it had heat. But that was billions of years ago. Now it's cold, dead, silent. And then there are the mountains. The moon has mountain ranges. Some of them are on the far side. They're not like Earth's mountains, formed by tectonic plates pushing together. Lunar mountains are the rims of ancient impact craters. When a large asteroid hits, it throws up walls of rock around the impact site. Those walls become mountains. Some lunar mountains are taller than anything on Earth. The peak of the Leibniz Mountains, near the moon's south pole, rises about 10,000 meters above the surrounding terrain, taller than Mount Everest above sea level. And they've stood there, unchanged, for billions of years. No erosion, no weathering, just stone, frozen in time. Take a deep breath. Imagine standing on one of those peaks, looking out over a landscape of craters, stretching to the horizon. The sky above you is black, even in daytime, because there's no atmosphere to scatter light. Stars are visible. The sun is a harsh white point of light. And if you turn around, looking for Earth, your home, your blue marble, you won't see it. It's hidden behind the moon. You are on the far side, the hidden side, the side that has never seen Earth. You are more alone than you've ever been. Let's talk about temperature, because the far side of the moon is not just visually different, it's thermally extreme. On Earth, we have an atmosphere. It acts like a blanket, trapping heat, distributing it, moderating temperature swings. When the sun sets, Earth doesn't instantly freeze. The atmosphere holds warmth. The moon has no atmosphere. None. Just vacuum. So when the sun rises on the moon, the temperature soars. In direct sunlight, the surface can reach about 127 degrees Celsius. That's 260 degrees Fahrenheit. Hot enough to boil water.
Hot enough to melt some metals. And when the sun sets, the temperature plummets. In darkness, the surface drops to about negative 173 degrees Celsius. That's negative 280 degrees Fahrenheit. Colder than anything on Earth, except maybe in a laboratory. That's a swing of 300 degrees Celsius in the span of a lunar day, which lasts about 29.5 Earth days. Now here's where it gets interesting. The near side of the moon faces Earth, and Earth, even though it's far away, provides a little bit of warmth, reflected sunlight, infrared radiation. Not much, but enough to make a tiny difference. The far side has no such comfort. When the sun sets on the far side, there's nothing. No Earth, no reflected light, just the cold of space. So the far side gets slightly colder than the near side during its night. And because the far side has more highlands and fewer dark maria, it also reflects more sunlight during the day, making parts of it slightly cooler even in daylight. It's a subtle difference, but it's there. The far side is, in some ways, the coldest part of the moon. And in the deepest craters, especially near the poles, where sunlight never reaches, the temperature stays at about -240 degrees Celsius all the time. These are called permanently shadowed regions. Scientists believe that ice might exist in these craters. The ice water brought by comets billions of years ago and preserved in the eternal darkness and cold. Water on the moon, hidden in the shadows of the far side. This isn't just scientifically interesting, it's practical. If humans ever establish a permanent base on the moon, water will be essential. Not just for drinking, but for making oxygen to breathe and hydrogen for rocket fuel. And some of the best places to find that water are in the permanently shadowed craters of the far side. Imagine that.
The hidden face of the moon, the loneliest place in our corner of space, might one day be home to human outposts. Research stations built in ancient craters. Astronauts drilling into ice that has been frozen for billions of years. The far side might not stay hidden forever. Take a breath. Let your mind wander through these temperature extremes, from boiling hot to freezing cold, in the span of 2 weeks. No atmosphere to cushion you, no wind, no clouds, just raw, unfiltered sunlight and the infinite cold of space. This is what the far side experiences every day, every year, for billions of years. And through it all, it remains patient, unchanging, waiting. Now, let's talk about something extraordinary, something that makes the far side of the moon unlike anywhere else in the solar system: radio silence. Here on Earth, we're bathed in radio waves all the time. Radio stations, television broadcasts, Wi-Fi signals, cell phone towers, satellites, GPS, even natural radio emissions from the sun and distant cosmic sources. Our planet is noisy. Electromagnetically speaking, we're shouting into space constantly, and that makes it very, very hard to listen. Radio astronomers, scientists who study the universe using radio waves, have a problem. They want to detect faint signals from the early universe, from the first stars, from distant galaxies, from mysterious cosmic phenomena. But Earth's radio noise drowns everything out. It's like trying to hear a whisper in a crowded stadium. So they build radio telescopes in remote places, deserts, mountains, islands, places far from cities and transmitters. But even in the most remote places on Earth, there's still noise. Radio waves bounce off the atmosphere, satellites pass overhead, the sun emits radio energy. There's one place in the solar system, though, where all that noise disappears: the far side of the moon. Think about it. When you're on the far side, the moon itself is between you and Earth.
The entire mass of the moon, 3,474 kilometers of rock, blocks every single radio wave coming from Earth. No television, no radio, no Wi-Fi, no cell phones, no satellites, nothing. And the moon has no atmosphere, so there's no ionosphere to reflect or distort signals. It's the quietest place, electromagnetically speaking, anywhere near Earth.
Radio astronomers dream about this place. They call it the ultimate radio quiet zone. From the far side of the moon, you could detect radio signals so faint, so ancient, that they've been traveling through space since the universe was young. Signals from the cosmic dark ages, the period after the Big Bang, but before the first stars formed. Signals that are completely impossible to detect from Earth. You could listen to the whispers of the infant universe. Several space agencies are already planning radio telescopes for the far side. China, in particular, has been making progress. In 2019, China landed the Chang'e 4 mission on the far side, the first soft landing ever on that hemisphere. And part of its mission was to test radio astronomy equipment. The idea is to eventually build a large radio telescope in a crater on the far side, protected, shielded, silent, and from there, to listen to signals that have been traveling for 13 billion years, to hear the universe as it was, when it was just a baby, to detect things we've never imagined, all because the far side of the moon is hidden, not just from our eyes, but from our noise. Take a moment, breathe deeply, imagine standing in a crater on the far side, in absolute radio silence, no human-made signals, no static, no interference, just the faint hiss of the cosmic microwave background, the echo of the Big Bang itself. You would be hearing the universe more clearly than anyone in history. That's the gift of the hidden side. It's not just a place we can't see. It's a place where we can see and hear things we've never been able to before.
Let's travel forward in time now. From the first blurry images in 1959, through the Apollo missions in the late 1960s and early 70s, into the modern era. Because humanity's relationship with the far side of the moon has been evolving, slowly, carefully, but consistently. After Apollo, interest in the moon waned for a while. The space race was over. The Soviet Union had collapsed. NASA's focus shifted to the space shuttle, to the International Space Station, to Mars rovers. But the moon never went away, and the far side, in particular, kept calling to scientists and engineers. In the 1990s and 2000s, new missions returned. Not manned missions, those were too expensive, too risky for the time, but robotic probes. Japan's Kaguya mission, launched in 2007, produced the most detailed maps of the moon ever made, including high-definition video of the far side. For the first time, the public could see what the Apollo astronauts had seen, crater after crater, in stunning clarity. NASA's Lunar Reconnaissance Orbiter, launched in 2009, went even further. It's still orbiting the moon today, mapping every square meter with incredible precision. It has imaged the far side in such detail that you can see individual boulders, tracks left by old Soviet landers, even the shadows in permanently shadowed craters. And then came China. China's space program has been growing steadily for decades, and in the 2010s, they set their sights on the moon, specifically the far side. In 2018, China launched Chang'e 4, a lander and a rover designed to touch down on the far side and explore it directly. But there was a problem. Remember, the far side of the moon never faces Earth. So if you land a spacecraft there,
you can't communicate with it directly. There's no line of sight. The moon itself blocks the signal. So China did something clever. In 2018, several months before Chang'e 4 launched, they sent up a relay satellite called quietest. This satellite doesn't orbit the moon.
Instead, it sits at a gravitational balance point called the L2 Lagrange point, about 65,000 kilometers beyond the moon on the far side. From there, quietest can see both Earth and the far side of the moon. It acts as a relay. Signals from the lander go to quietest, and quietest sends them to Earth. It's like shouting around a corner using a mirror. On January 3, 2019, Chang'e 4 landed in the von Karman crater, inside the South Pole Aitken Basin, the first soft landing on the far side of the moon. The first time a rover named U-22, or Jade Rabbit 2, rolled across the hidden hemisphere, and the images it sent back were breathtaking. The landscape was exactly as expected, cratered, rough, gray. But seeing it up close from the surface was different. The rover's camera showed the texture of the soil, the shapes of nearby rocks, the way shadows fell in the harsh sunlight. And it showed something else, something subtle but profound: loneliness. In every image from U-22, the horizon is close. The moon's small size means the horizon is only about 2.4 kilometers away if you're standing on the surface. So everything feels enclosed, intimate. You're in a small bubble of visible terrain, surrounded by an endless expanse you can't see. And there's no Earth in the sky to remind you of home. Just the black sky, the distant sun, and the knowledge that you are standing where no one has stood before, where no one for billions of years has even looked. Chang'e 4 is still there. U-22 is still roving, slowly, carefully, studying the rocks and soil. It has lasted far longer than its original mission plan, and it keeps sending back data. Data about the composition of the far side, about the structure of the crust, about the history of impacts. Every discovery adds another piece to the puzzle of the moon's history, and by extension, Earth's history. Because the moon is Earth's companion, its partner. What happened to the moon happened near Earth. The same bombardment that scarred the moon also hit Earth. But Earth has weather and tectonics and life. Earth's scars have been erased. The moon remembers. And the far side especially remembers. Take a slow breath. Imagine U-22 right now, at this very moment, sitting in a crater on the far side, its solar panels soaking up sunlight, its instruments measuring, analyzing, recording. No humans nearby, no mission control watching in real time. There's a delay of several seconds as signals bounce through quietest. Just a small robot, alone on the hidden side of the moon, doing science. There's something beautiful about that. Now, let's talk about the future, because the far side of the moon is about to become very important. As I speak these words, multiple space agencies and private companies are planning missions to the moon. Not just flybys or orbiters, but landings, bases, permanent human presence. NASA's Artemis program aims to land astronauts on the moon again, this time including the first woman and first person of color by the mid-2020s. The goal isn't just to visit, it's to stay, to build infrastructure, to establish a sustainable presence. China has similar plans. They're working toward a lunar research station, possibly in partnership with Russia and other nations, a base where scientists can live and work for extended periods. And much of the focus is on the South Polar region. Why?
because that's where the water is, in those permanently shadowed craters we talked about earlier. But here's the thing. The south polar region of the moon includes parts of the far side. So future lunar bases, habitats, labs, landing pads, power stations might be built on the hidden hemisphere. Imagine that. Humans living on the far side of the moon, waking up to a sky without Earth, working in craters they have never seen our home world. They would be the loneliest pioneers in history. But they wouldn't just be there for the sake of being there.
They'd have jobs, important jobs. First, there's the radio astronomy we talked about. A telescope on the far side could revolutionize our understanding of the early universe. Scientists from around the world would compete for observation time. Second, there's resource extraction. The moon has materials we need: metals, oxygen locked in rock, helium-3, which could potentially be used for fusion energy. Mining the moon might sound like science fiction, but it's being seriously discussed. Third, there's the moon as a stepping stone. If we want to go to Mars, or to the asteroids, or deeper into the solar system, launching from the moon is much easier than launching from Earth. The moon has 1/6 the gravity and no atmosphere. You need far less fuel. So a base on the moon, especially on the far side, away from Earth's clutter, could become a hub, a port, a gateway to the rest of the solar system. And the far side has one more advantage. It's protected. Think about it. If something catastrophic happened on Earth, a nuclear war, an asteroid impact, a pandemic worse than anything we faced, a base on the far side of the moon would be shielded, not just by distance, but by the moon itself. 3,474 kilometers of rock between them and whatever disaster struck Earth. It's morbid to think about, but it's also practical. The far side of the moon might one day be the safest place in the solar system for human survival. Some futurists even talk about building vaults there, archives of human knowledge, DNA banks, seeds, art, history. Everything we've created, stored in the deepest craters, protected by lunar rock and vacuum, preserved for thousands or millions of years. A backup for human civilization, on the side of the moon that never sees Earth. There's poetry in that, isn't there? The idea that our greatest achievements, our most precious knowledge, might one day be stored on a world that has spent billions of years turned away from us.
As if the moon has been waiting, keeping a space ready just in case we ever needed it. Take a breath. Let your imagination drift. Picture a future where lights flow in lunar craters, where astronauts walk across ancient regolith, doing their work under a sky of stars, where radio telescopes listen to the oldest signals in the universe, where humanity has a foothold on another world. And that foothold is on the hidden side, the side that was secret for so long. It won't be secret anymore. But let's return to the present, because there's something we need to talk about. The far side of the moon is not the dark side. This is one of the most common misconceptions about the moon. People hear the far side, and they think it's always dark, always in shadow, that the sun never shines there. But that's not true. the far side gets just as much sunlight as the near side. The moon rotates, remember? One rotation every 27.3 days. So every part of the moon experiences day and night. When it's daytime on the far side, it's nighttime on the near side. When we see a new moon from Earth, when the moon is dark in our sky, that's because the far side is facing the sun. It's lit up, bright, baking in sunlight. We just can't see it. The term dark side of the moon probably comes from the idea of unknown or hidden. Not literally dark, like when we say a dark secret or kept in the dark. But the confusion persists. And honestly, it's understandable. Because from our perspective, the far side might as well be dark. We can't see it. For most of history, we didn't know what was there. In a way, it was dark. Just not literally. But there is one place on the far side that is literally dark. All the time. The permanently shadowed craters. These exist at both poles. But there are several in the South Polar region that touch the far side. Deep craters where the sun never, ever shines.
Not because the sun doesn't exist, but because the walls of the crater are so tall, and the sun at the lunar poles is so low on the horizon that sunlight can't reach the bottom. These craters have been in darkness for billions of years. Scientists call them cold traps because anything volatile, water, carbon dioxide, ammonia, that wanders into these craters gets trapped, frozen, preserved. And that's where we think the ice is. Probes have detected hydrogen signals from these craters. Hydrogen usually means water, so we're pretty confident there's ice down there. But we haven't sampled it directly. Not yet. That's one of the goals of future missions, to send a rover into one of these permanently shadowed craters, drill into the ice, and bring back a sample. Imagine that moment. A rover descends into a crater that has been dark for 4 billion years. Its lights flick on, the first light this place has seen since the solar system was young. It drills into the ice, extracts a core, and in that core, scientists could find water molecules that fell from comets when dinosaurs' ancestors hadn't even evolved yet. Water older than life on Earth, preserved in darkness on the hidden side of the moon. Take a moment, breathe slowly. Let the scale of time wash over you. 4 billion years. The same ice, frozen in place, while the Earth changed completely, while continents formed and broke apart, while oceans rose and fell, while life emerged, evolved, spread, thrived. And through it all, this ice waited, in the dark, on the far side, waiting to tell its story. There's something philosophical about the far side of the moon, something that goes beyond science and engineering.
It's about perspective. For all of human history, we've looked up at the moon and seen the same face. We've named the features: the Sea of Tranquility, the Sea of Serenity, the crater Copernicus, the crater Tycho. We've written poems about the moon, songs, stories.
We've used it to mark time. Months are based on the moon's cycle. We've associated it with emotions, lunacy, romance, mystery. The moon has been part of our culture, our mythology, our collective consciousness. But we only knew half of it. There was another half, always there, always turning, always existing, but hidden from us. What does that mean? It means that even something as familiar as the moon has secrets. Even something we see every night has a side we cannot see. And maybe that's true for everything. Every person has a hidden side, parts of themselves they don't show, thoughts and feelings and experiences that are theirs alone. Every place on Earth has a history we don't know, layers of time buried beneath our feet. Every moment has a context we can't perceive, things happening simultaneously that we'll never witness. The far side of the moon is a reminder, a symbol. It tells us there is always more than what you can see. There is always mystery, always something hidden. And that's not a bad thing. Mystery is what drives us. Curiosity is what makes us human. The far side of the moon was hidden for billions of years, and that made it precious. It made it worth exploring. When Luna 3 sent back those first blurry images in 1959, the mystery didn't disappear. It deepened, because now we knew there was something different over there, something strange, something that demanded explanation. And when Apollo 8 astronauts saw it with their own eyes, the mystery transformed again. It became personal, real, a place they had been, a place they could describe. And when Chang'e 4 landed on it, touched it, rolled across it, the mystery became tactile, scientific. We could measure it, analyze it, understand it. But even now, with all our maps and missions and data, the far side of the moon is still mysterious. Because mystery isn't just about not knowing, it's about recognizing the depth of what there is to know. Every rock on the far side has a story.
Every crater is a moment frozen in time. Every grain of regolith is a fragment of ancient impacts, ancient heat, ancient violence. We can spend 100 years studying the far side and still not know everything, and that's beautiful. Take a deep breath. Close your eyes. Think about the moon right now if it's nighttime where you are, or imagine it if it's day. That familiar face looking down at you, the same face humans have always seen. But remember, there's another face, turned away, hidden, scarred, cold, and it's still there, still turning, still existing, whether you see it or not. Let's talk about some of the specific features of the far side, the craters and basins that make it unique. We've already mentioned the South Pole Aitken Basin, the giant impact scar that dominates the southern far side. But there are others. There's the Korolev crater,
named after Sergei Korolev, the father of the Soviet space program. It's about 437 kilometers in diameter. From orbit, it looks like a massive circular scar with a raised rim and a relatively flat floor. What's interesting about Korolev is that it's one of the few large craters on the far side that has a small patch of mare, dark volcanic rock, in its center. This suggests that the impact that created Korolev was powerful enough to crack through the thick far side crust, allowing lava to seep up. It's a reminder that the division between near side and far side isn't absolute. There are exceptions, overlaps. The moon is complex. Then there's the Tsiolkovsky crater, named after Konstantin Tsiolkovsky, the Russian rocket scientist who dreamed of spaceflight long before it was possible. Tsiolkovsky is about 185 kilometers in diameter, and it's one of the most striking features on the far side. From above, it looks like a dark pool surrounded by bright highlands. The crater floor is filled with mare, dark, smooth, frozen lava.
Why did lava fill this crater and not others nearby? Scientists aren't entirely sure. Maybe the impact was at just the right angle, at just the right time, when the moon's interior was still molten enough for lava to flow. Or maybe there's something about Tsiolkovsky's location, some quirk of the crust, some weakness that allowed the lava through. Either way, it's beautiful, a dark eye on a pale face. There's also the Daedalus crater, named after the Greek inventor who built wings to fly. It's about 93 kilometers across and sits near the lunar equator on the far side. Daedalus has a prominent central peak, a mountain in the middle of the crater, formed when the rock rebounded after the impact. This peak is about 2,000 meters tall. From the crater floor, it would loom over you like a monument. Standing at the base of that peak, looking up, you'd be looking at a mountain created in seconds, formed by unimaginable violence, and then frozen, unchanged for billions of years. No wind has eroded it, no rain has worn it down. It's exactly as it was the moment it formed. That's the eerie thing about the moon. Everything is preserved. Every feature is a snapshot of a moment in time. On Earth, landscapes change. Mountains rise and fall. Rivers carve valleys. Glaciers grind rock to dust. On the moon, nothing changes. The landscape is a museum. Every crater, every boulder, every grain of dust is ancient. And on the far side, especially, where human activity has been minimal, the landscape is pristine, untouched. It's like walking through a library where every book is billions of years old, and the books are written in stone. Take a breath. Let your mind wander across these craters: Korolev, Tsiolkovsky, Daedalus, each one a scar, each one a story. And there are thousands more, tens of thousands, more craters on the far side than anyone has counted. Each one unique, each one waiting. Now, let's talk about something strange.
Something that scientists are still trying to understand. The moon's center of mass, the point where all its mass is balanced, is not at its geometric center. It's offset toward Earth by about 2 kilometers. That might not sound like much, but for a body the size of the moon, it's significant. What this means is that the moon is slightly heavier on the near side. There's more mass there, more density. Why? There are a few theories. One idea is that the maria on the near side, those dark volcanic plains, are denser than the highlands. Basalt, the rock that makes up the maria, is heavier than the anorthosite that makes up the highlands. So the near side, with its large maria, has more dense rock, and that pulls the center of mass toward Earth. But that doesn't fully explain it, because the offset existed before the maria formed. We know this because computer models of the moon's early history show the offset must have been there from the beginning. So maybe it's related to the moon's formation. When the moon formed, probably from a massive impact between Earth and a Mars-sized object, the debris that became the moon was hot, molten. It cooled over time, and as it cooled, heavier elements sank toward the center. But the moon was already in orbit around Earth by this point, and Earth's gravity was pulling on it, strongly. So maybe as the moon cooled, the side facing Earth ended up with slightly more of the heavier elements, pulled there by Earth's gravity, concentrated there, and that created the offset. Another theory suggests that the far side crust formed thicker because it cooled faster. The near side, facing Earth, received more heat from Earth's own warmth when Earth was still molten, so it stayed hotter longer, and that allowed the near side crust to form thinner. Thinner crust means lava could break through more easily, creating Maria. Thicker crust on the far side means no Maria.
And thinner crust also means more density, because the mantle beneath the crust is denser than the crust itself. So the offset and the difference between near and far side might be connected. The moon's hidden face might be different because of Earth, because of our planet's influence from the very beginning. In a way, Earth made the far side what it is. We shaped the moon, and the moon shaped us by stabilizing Earth's tilt, creating tides, influencing life's evolution. We're partners, locked in a gravitational dance that has lasted for 4.5 billion years. And the far side is the part of the moon that never looks at us, but it exists because of us. There's something poetic about that. Take a moment, breathe deeply. Think about the connection between Earth and Moon, how they formed together, how they've shaped each other, how they continue to influence each other even now. The moon tugs on Earth's oceans, creating tides. Earth tugs on the moon, keeping it locked, keeping one face always turned toward us. We cannot escape each other. And the far side, the hidden side, is the part of the moon that bears the mark of that eternal connection. Let's talk about what it would feel like to stand on the far side. Imagine you're an astronaut. You've traveled to the moon, landed in a crater on the far side. You step out of your lander onto the surface. What do you feel? First, the gravity. The moon's gravity is about 1/6 of Earth's. So if you weigh 180 pounds on Earth, you weigh 30 pounds on the moon. Walking feels strange. Each step is a small leap. You have to move carefully, deliberately. If you push off too hard, you'll fly up, and it'll take a moment to come back down. The Apollo astronauts described it as bouncing, like being underwater but without the resistance. Now you look around. The ground is gray. Not a warm gray, but a cold, lifeless gray. The regolith, the lunar soil, is fine, like powder, but it's not soft. It's abrasive, sharp.
Made of tiny shards of glass, created by eons of meteorite impacts. It clings to your boots, gets into every crevice of your suit. The horizon is close, about 2.4 kilometers away. You're standing in what feels like a bowl. The ground curves away from you in all directions, and above you, the sky is black, even though the sun is shining, even though it's daytime. On Earth, the sky is blue because our atmosphere scatters sunlight, but the moon has no atmosphere, so there's nothing to scatter the light. The sky is just space, black, infinite, and the stars are visible, even in daylight, sharp points of light against the blackness. You look for Earth, but it's not there. You turn around, scan the entire sky. Nothing, because you're on the far side. Earth is on the other side of the moon,
Behind you, blocked by 3,474 kilometers of rock. For the first time in your life, Earth is not visible. And that's when it hits you. The loneliness. You're standing on a world that has never seen your home. You're in a place where, if you look up, you see only stars. No familiar blue dot, no continents, no oceans, no clouds. Just you and the moon and the universe. It's terrifying, and it's beautiful. The sun hangs in the sky, harsh and white. It doesn't twinkle, it doesn't shimmer. It's just there, a point of intense light, and the shadows are absolute. On Earth, shadows are soft because light scatters in the atmosphere. But on the moon, shadows are pure black. If you step into a shadow, you can't see your own feet. The contrast is extreme, bright light and total darkness, side by side, with no transition. You move carefully. Check your oxygen. Check your suit temperature. It's getting hot in the sunlight, but the suit's cooling system is working. You look down at the ground. There are no footprints here except yours. No human has ever walked where you're walking. And your footprints will last for millions of years.
Because there's no wind to blow them away, no rain to wash them away. You are leaving a mark that will outlast your civilization. That thought is staggering. You kneel down, pick up a rock. It's light in your hand. Everything feels lighter here. You turn it over, look at it. This rock is older than any rock on Earth. Older than life, older than oceans. It has been here, in this spot, for billions of years, undisturbed, until you picked it up. You put it down gently, respectfully, and you stand, look around one more time, at the craters, the mountains, the black sky, the distant sun. You're on the far side of the moon, the hidden side, the loneliest place any human has ever stood. And it's quiet, so quiet. No wind, no sound, just the faint hiss of your own breathing inside your helmet. You could stay here for hours, days, just standing, thinking. But your oxygen is limited. Your mission has a schedule, so you take one last look, memorize the scene, and you turn back toward the lander. But you know you'll never forget this. No one who has stood here ever could. Take a deep breath. Imagine that silence, that isolation, that profound, overwhelming sense of being far from home. That's what the far side feels like. Not just scientifically, emotionally. It's a place that changes you. Now, let's talk about the future of lunar exploration, because the far side is about to become much less lonely. NASA's Artemis program is planning a series of missions to the moon over the next decade. Artemis 2 will fly astronauts around the moon, similar to Apollo 8, but with modern technology. Artemis 3 will land astronauts on the surface, near the South Pole most likely, and some of those landing sites are on the edge of the far side. If that happens, it'll be the first time humans have set foot on the far side since, well, ever. No Apollo mission landed on the far side. They all landed on the near side, where communication with Earth was easier. But with modern technology, relay satellites like China's Kwokcha, communication with the far side is possible now. So future astronauts will walk where no one has walked. They'll see the far side with their own eyes, from the surface. And they'll do science. They'll collect samples, drill into the regolith, set up experiments, maybe even plant a radio telescope. China is also planning more missions. Chang'e 6 is designed to return samples from the far side. It launched in 2024 and successfully brought back rock and soil from the hidden hemisphere.
the first time far-side samples have been returned to Earth. Scientists are analyzing those samples right now, looking at the minerals, the isotopes, the chemical composition. Every grain of dust tells a story. And there are more missions planned. Chang'e 7 will explore the South Polar region. Chang'e 8 will test technologies for building a lunar base. Russia and China are talking about a joint international lunar research station, a permanent base, with modules for living, working, researching. And some of that base might be on the far side. India too has lunar ambitions. Their Chandrayaan missions have already made important discoveries, like confirming water ice at the poles. Future missions might land in far-side regions. Even private companies are getting involved. SpaceX, Blue Origin, and others are developing lunar landers. Some of those landers will carry scientific payloads to the far side. In 20 years, the far side of the moon might be busy. Rovers rolling across ancient craters, astronauts setting up equipment, radio telescopes listening to the universe, mining equipment extracting water from ice. It won't be hidden anymore. But will it still be special? I think so, because even when we're there, even when we've mapped every crater and analyzed every rock, the far side will still represent something. It will still be the place that was hidden for so long.
The place that humans couldn't see for all of history until we finally built the technology to go there. It will still be the loneliest place in our corner of space, the place where Earth disappears, where you're truly, profoundly far from home. And I think we'll always treat it with a kind of reverence, because the far side of the moon taught us something important. It taught us that there's always more to discover, that even the familiar has secrets, that the universe is full of hidden faces, waiting for us to find them. Take a breath. Let your thoughts drift forward in time. Imagine a future where humans live on the moon, where children are born there, where the far side is no longer mysterious, but home. What will they think, those future lunar colonists, when they look up at Earth? Will they feel the same loneliness the Apollo astronauts felt? Or will they feel something else? Pride, maybe. Wonder. A sense of accomplishment. They'll know that their ancestors, people like you and me, looked up at the moon and dreamed, wondered, built rockets and took risks and explored the unknown. And because of that, they get to live on another world, on the far side, the hidden side, the side that waited billions of years to be found. There's one more thing we need to talk about, the poetry of the far side. Because beyond all the science, beyond the missions and the data and the future plans, there's something deeply human about the far side of the moon. It's a metaphor. For thousands of years, humans have looked at the moon and seen themselves. We've projected our emotions, our dreams, our fears onto that silver disk in the sky. The moon has been a symbol of change, waxing and waning, never staying the same. A symbol of romance, lovers meeting under moonlight. A symbol of mystery, the moon goddess, the werewolf, the lunatic. But we only knew half the story. The side we could see became familiar, comfortable, known.
But the other side, the far side, remained hidden, unknown, mysterious, and that made it powerful. The far side became a symbol of the unknowable, the unreachable, the part of ourselves or the universe that we can't access. It's the shadow self, the unconscious, the parts of reality that exist but remain hidden from view. In literature, the far side of the moon has been used as a setting for secrets. In Pink Floyd's famous album, The Dark Side of the Moon, it's a metaphor for madness,
for the parts of the mind that are hidden even from ourselves. In science fiction, the far side is often where aliens hide, or where ancient structures are found, or where humanity's darkest experiments take place. Why? Because it's hidden, because it's other, because it represents everything we don't know. But here's the beautiful thing. We've been there now. We've seen the far side. We've mapped it, photographed it, landed on it. And you know what we found? Not aliens, not ancient cities, not some cosmic secret that changes everything. We found a landscape, craters, rocks, ice, mountains. Beautiful in its own way, scientifically important, geologically fascinating, but ultimately just another part of the moon. And that's the real lesson. The far side was never truly dark. It was never truly mysterious in some supernatural sense. It was just hidden. And when we finally looked, we found something real, something natural, something we can understand. The mystery didn't disappear, but it transformed. From "what is that?" to "how did that form? What does it mean? What can we learn from it?" That's the journey of science, of exploration, of being human. We see something we don't understand. We wonder, we dream, we build tools, we go there. And when we arrive, we find that reality is even more interesting than the mystery. Because reality has depth, it has layers, it has causes and effects, and stories that go back billions of years.
The far side of the moon isn't just a hidden face. It's a chronicle of the early solar system, a record of impacts and lava flows and cooling rock, a place where we can study the history of our cosmic neighborhood. It's a testing ground for future exploration, a place to practice living on another world before we go to Mars or beyond. It's a radio quiet zone where we can listen to the universe without interference. It's a symbol of how far we've come, from wondering what's over there to actually going over there and finding out. And it's a reminder of how far we still have to go, because the moon is just the beginning. There are hidden sides everywhere. The far side of Mars, the subsurface oceans of Europa, the depths of Titan's methane lakes, the cores of distant exoplanets. Every world has secrets. Every corner of the universe has something we haven't seen yet. And the far side of the moon taught us that those secrets are worth discovering, not because they'll always be what we expect, but because the act of discovering them, the journey from unknown to known, is what makes us human. Take a slow, deep breath. Let your mind settle. Let the image of the moon, both sides, near and far, fill your thoughts. You've only ever seen one side with your own eyes, but now you know the other side is there, turning, existing, waiting, covered in craters, bathed in sunlight and shadow, cold and ancient and real. It's not dark, it's not mysterious in some magical sense, but it's still special because it was hidden, and now it's not, and that changes everything. So here we are, at the end of our journey to the hidden side of the moon. We've talked about tidal locking, how the moon became trapped, always showing us the same face. We've talked about the first images from Luna 3 and the shock of seeing a landscape so different from what we expected. We've talked about the Apollo astronauts floating in radio silence, seeing the far side with their own eyes. We've talked about the craters, thousands of them, layered and overlapping, a record of ancient violence. We've talked about the temperature extremes, the permanently shadowed craters, the possibility of ice. We've talked about the radio quiet zone and the dream of building telescopes there to listen to the early universe. We've talked about China's Chang'e 4, the first mission to land on the far side, and the relay satellite that made it possible. We've talked about the future, the bases, the missions, the humans who will one day live on the hidden side. And we've talked about the poetry, the metaphor, the meaning. But there's one last thing to say. The far side of the moon has been there all along. For 4.5 billion years, it has been turning, existing, real. It didn't need us to discover it to be important. It was always important. Every crater tells a story about the early solar system. Every rock holds clues about planetary formation. Every grain of ice in a shadowed crater is a time capsule from the age of comets. The far side has been patiently holding these stories, waiting. Not for us specifically. It doesn't care about us, but waiting nonetheless. And now, finally, we're reading those stories. We're listening. We're learning. And that's a profound thing, because it means the universe is knowable. Reality is understandable. The hidden can be revealed, not through magic, not through divine revelation, but through curiosity, through effort, through building rockets and cameras and rovers and sending them across the void to touch another world. That's human achievement. That's what we're capable of. And the far side of the moon, the hidden side, the lonely side, the side that never sees Earth, is proof. So the next time you look up at the moon, remember, you're seeing half of it. The other half is there, right there, just on the other side, covered in craters, bathed in starlight, cold and ancient and beautiful. It can't see you.
But you know it's there. And maybe that's enough. Maybe knowing is enough. Maybe the joy of discovery, the satisfaction of understanding, is the real gift. The far side of the moon taught us that, and it will keep teaching us. For as long as we keep looking, keep wondering, keep exploring. So sleep well, traveler. Let the moon watch over you, both sides of it, the side you can see and the side you can't. They're both there, both real, both part of this strange, beautiful universe we're trying to understand. One patient crater at a time. Safe travels and sweet dreams. May your mind wander to hidden places, and may you always find your way back home.